I am Heather Wilkens, Manager of Business Development at ATA Engineering. I'm pleased to be here today to discuss our Phase 2 SBIR project titled Rotorcraft Integrated Electro-Optic Infrared, or EOIR, Plumes and Effects Signature Modeling, which is NAVIR Topic 181-010. The principal investigator for this project is Dr. Nicholas Revelis, who works out of our office in Huntsville, Alabama. I'll give you a quick overview of ATA's capabilities, and then I'll dive right into this exciting project. ATA provides innovative solutions through analysis and test-driven design by focusing on the engineering needs of manufacturers in addressing their cost, quality, and time-to-market challenges for mechanical and aerospace systems. ATA is an all-employee-owned small business, which really promotes an entrepreneurial can-do attitude. We now have over 180 employees, the majority of whom hold advanced degrees. We use testing and analysis coupled with computer-aided engineering and mechanical engineering software to solve problems in the aerospace, defense, themed entertainment, and industrial markets. We're experts in applying advanced mechanical engineering software to design, test, and analyze mechanical engineering structures, with particular expertise in complex, highly engineered structures subject to severe dynamic loads. Besides our headquarters in San Diego, where I'm located, we also have offices in Los Angeles, the San Francisco Bay Area, Denver, Albuquerque, Huntsville, and Washington, D.C. So we can provide local, full-service capabilities and personal support to our customers. In the upper right corner, you'll see the Mars rover Curiosity, for which we provided analytic support for nearly 4 years ahead of its launch. ATA continued our legacy of supporting the exploration of the Red Planet by supporting NASA JPL's Mars 2020 Perseverance rover. Over 50 ATA engineers participated in mechanical engineering test and analysis services for its subsystems and components. So let's dive into the topic of our presentation. The Navy requires improvements in EOIR analysis for rotary wing platforms, specifically for both countering adversarial technologies as well as ensuring that our own aircraft have enhanced survivability. The sponsoring program for this work is PMA 261, so the heavy lift helicopters, with an emphasis from the CH-53K. This work is broadly applicable and has also received support from PMAs 275, 299, and 272. Our goal with this work is to improve EOIR signature estimates to enhance survivability for Navy rotorcraft platforms. There's a lot of technology out there today that can obtain an EOIR signature prediction if you already know what the temperature of the vehicle is, and you do not necessarily care what is happening with the engine plume. We're looking to expand that to be able to include not only the body and environmental effects, but also to include the engine plume, especially any asymmetry that may develop due to the rotorcraft's unique flow field. Any solution has to be able to leverage existing and widely validated and verified tools from the EOIR signature modeling community, which is mainly the JANF exhaust plume and signatures group. Additionally, we're focused on making sure the solution provides enhanced realism to the simulations and has a multidisciplinary approach that offers improved functionality over any single code by itself. Finally, providing a user-friendly graphics user interface, or GUI, is enormously beneficial to the end user. What we show on the bottom is a computational fluid dynamics simulation on the left, which has been converted and mapped to something that's EOIR results on the right. The ability to go from the CFD solution to an IR solution is an example of the type of thing we're looking to provide. ATA's solution is the Rasp Toolkit, which stands for the Rotorcraft Advanced Signature Prediction Toolkit. What it does is it exists as middleware between CFD analysis or other aerodynamics analysis and the EOIR analysis. It sits in between the two in order to leverage the strengths of both tools to provide a very high fidelity analysis of plume effects and signatures while maintaining support for the previously existing body radiation environments and related or similar functionality. The Rasp Toolkit provides an analyst the ability to have more insight into observability of rotary wing platforms. It will help during the design phase. You can start to examine what will affect the observability of an aircraft and design good countermeasures. It can also help with threat assessments and even inform weapons and sensor development with the underlying technology. The tool currently leverages existing well-validated software. Our baseline CFD tool is NASA Langley's Fun3D Solver, which is very well validated for rotary wings aerodynamic simulations. We're also working toward incorporating support for the DoD's Create AV Helios software. On the EOIR modeling side, we're working towards support for Spirits, We currently have support for SPERC, and we have a prototype support for the flight solver. It's also relatively easy to support other CFD and EOIR software packages since we designed the Rasp Toolkit on an open architecture paradigm. This means that the source code will be available at no cost to qualifying organizations. What we show on the bottom right is an example of our GUI applying different surface materials to a CFD model. For example, the windows are illustrated in one of the blue shades. Normally, with a CFD model, you wouldn't necessarily care about some of these features. For example, on the fuselage body, you might combine everything into one surface. But the Rasp Toolkit helps to essentially paint the CFD model with the correct material properties for the EOIR analysis. We are currently moving toward a fixed wing validation case. It's a standard validation case, and we're working with the Army's Rotorcraft group at Moffett Field to coordinate and perform that validation effort. We're also coordinating our work with the developers at the DoD's Helios tool at Moffett Field, which we're looking to integrate in the option period. Once we complete the fixed wing validation, the next step is to begin providing evidence of rotorcraft validation. Currently, we have a functional prototype of the GUI that supports the toolkit, and it will be completed by the end of our base period this year. We have a conjugate heat transfer solver for transferring the thermal loads into the fuselage that is currently undergoing verification. In the option period, we'd like to integrate the Rasp Toolkit with the Helios software, and we would see actual program use occurring after that in 2023. Now let's discuss 5 key features that our solution offers. First, the Rasp Toolkit is integrated with existing well-validated government software codes, which means that the tools that underpin it are already familiar to users, at least in the respective disciplines. They're tools that the government can use at no cost, which brings immediate financial savings. ATA built the Rasp Toolkit with a variable modular fidelity approach that allows the user to swap model fidelity as well as turn on and off certain effects. This enables the end user to apply the most appropriate model for a given problem. Therefore, you're not underpredicting when you have a need for a higher fidelity model and vice versa. If you have limited data, for example, for an adversary's vehicle for which we only have partial data, we're not trying to invent input data where none exist. That variable fidelity enables very efficient analysis. One thing that the analyst might not have, for example, for an adversary's vehicle, would be a model of the underlying structure. This brings up our third key feature, which is the conjugate heat transfer modeling capability. Within the rotorcraft flow field, the engine plume can impinge on a stabilator or a tail boom, and it can be time varying due to the nature of the wake. If the blades are moving, so too is the engine plume, which changes where it impinges. And if you have a thermal model of the fuselage, we can model that and correctly resolve the time-varying signature due to the interior thermal effects. That provides a more physical understanding with improved accuracy by obtaining the hard body temperatures with a structure that can absorb and emit heat. So when the plume impinges onto a spot of the structure, it gets hotter, and if the plume moves away from that spot, it cools due to convective effects. Without this capability, you would typically assume an adiabatic wall boundary condition where the temperatures vary instantaneously, which we know is not physically accurate. The fourth feature that we offer is improved modeling capability for the electro-optic side, specifically for Geiger mode LiDAR systems. This has been developed by our subcontractor, Iris Technologies, who have included distortion effects caused by turbulence on the LiDAR return. Their focus has been on enhancing the signature prediction for detection and ranging. The final key feature is an improved performance on the electro-optic solver leveraging high-fidelity CFD simulations. These simulations utilize highly refined fluid dynamic meshes, which consist of billions of volumes that leverage the EOIR solver directly, which would otherwise incur large computation costs to process. It would be straightforward to transfer these results directly to a much coarser mesh, but without proper care, there can be a smearing effect, and gradients within the flow field important for electro-optics may be lost. We've developed the ability to transfer that data onto a much coarser data set that does an excellent job of preserving the original data. We've demonstrated the ability to obtain a nearly identical solution with a 2-order magnitude of reduction in data size. This helps to recover the original runtimes that you're used to for electro-optic or infrared solvers. ATA is very excited to transition the Rasp Toolkit to the Navy. During our ongoing period of performance, ATA is continuing to develop and validate the prototype to create a polished final tool. By the end of 2022, we plan to have an advanced prototype GUI with simulation orchestration modules, conjugate gradient heat transfer capability, and a statistical turbulence model for electro-optics. It is an open source software that ATA will provide to qualifying organizations at no cost, and we can have two different variants, one for desktop computers and the other for high-performance computing centers. If you're already leveraging, for example, the DoD HPC computers for CFD calculations, we can put the Rasp Toolkit on those very same systems to eliminate data transfer times. The CFD and EOIR communities are already familiar with these tools, and we expect them to leverage this and implement their own features and enhancements that work to improve their workflow. Furthermore, the toolkit is easily extensible, so we expect additional compatibility with other CFD and signature analysis tools. And we're currently working toward integration with the DoD Helios framework. As an example, ATA intends to develop compatibility with the Loci Chem CFD solver for our own internal use, and we are confident that other groups will have tools that they'll want integrated with this toolkit as well. In terms of commercialization and market opportunities, our primary path involves developing a user base for the Rasp Toolkit with involvement from military rotary wing platforms. ATA intends to place emphasis on special operations where aircraft are derivatives of other platforms and survivability is of key importance. We see a good fit with the Rasp Toolkit wherever design modifications are key to survivability. Additionally, we anticipate that new vehicles under current development, such as those for future vertical lift, will want to leverage the Rasp Toolkit. Secondary applications include airborne sensors and weapons seeker analysis, applications to countermeasures, and potential use with commercial aircraft that may face risk from older but widely disseminated air defense systems. Finally, Rasp was designed with customization in mind, and we anticipate interest in customizing the software for prime contractors who desire specific interfaces. ATA expects the technology to transition well since we anticipate a robust Rasp Toolkit user group will develop relatively quickly. Users within the respective communities already know the underlying software tools on the CFD and EOIR solver sides, and the Rasp Toolkit is a natural bridge between these two disciplines for non-expert users. ATA anticipates multiple ways that we will commercialize the technology. Since we're not charging for the software and its open architecture, we need other commercialization routes. ATA is more of a consulting company than a software development firm, so using the software to assist our customers is a natural extension to what we already do and how we operate. Likewise, when we perform methods development for our customers, we give away the technology, methods, and algorithms. This may sound like an unusual business model, but we have found that in doing so, not only do we delight our customers, but they typically return to us with harder and more challenging problems. This is why we're not trying to corner a small market with our software, and instead are giving it away and seeking to help others use it. In that vein, we anticipate providing training courses, whether virtual or in person, during non-COVID times, we hope. And we should note that we are trying to get a Rasp Toolkit tutorial in the GenF 2022 conference. So ATA can help with signature analysis either directly through hands-on computations or indirectly by ensuring that the analysts performing the work have the tools they need to complete the job. Our software is open and free to modify, but as the principal developers, we will be in a position to customize it for applications more efficiently than someone who's not directly familiar with how it works. Finally, one of the things that ATA does really well is end-user software support for various commercial software tools. We see an analogous opportunity with the Rasp Toolkit to offer our customers excellent support. We welcome you to visit Nicholas and I in our virtual booth here at the Department of Navy Forum for SBIR STTR Transition, or please feel free to reach out by email or phone if you'd like to learn more about our capabilities. Thank you so much for your interest in ATA and our Rotorcraft Signature Modeling Project.